Example number 4, where it says the inequalities associated with strictly positive polynomials, and then they give us a function f of x is equal to x squared plus 7 times the quantity 2x squared plus 1. And then it says have unusual solution sets, and then it says we use the figure to figure out the solution sets for this. And so graphically, this thing looks a little different. So first of all, if I were to graph this, this is a 4th degree polynomial, and what that means is that my 4th degree polynomial is going to cross, or has the potential of crossing the x-axis 4 times. So I've got x to raised to the 2nd power times an x raised to the 2nd power. So that means it's a 4th degree polynomial. That means that I have the possibility of having 4 real solutions or 4 x-intercepts. Now, because it's positive, where does it come? Because it's an even degree polynomial, where does it start? At the top or the bottom? Starts at the top. So we might have one of these deals where it comes down, crosses again, and goes up. We might have something like that. It's a possibility. Okay. We don't really know. We'd have to set the. We'd have to graph this thing to see what it looks like. So, however, they wanted us to consider a couple of things. So, for example, they wanted us to consider, like, what does this look like? If I say x squared plus 7 times 2x squared plus 1 equals 0. Well, now, if I solve this, I end up with x squared plus 7 equals 0, and then 2x squared plus 1 equals 0. And so when I solve that, I get x is equal to plus or minus the square root of negative 7. Right? And then over here, I get x is equal to the square root of negative 1 over 2, plus or minus. Right? And so what does that tell us? What does that tell us? Well, that tells us graphically there's no real solutions. In fact, we have 4 complex solutions. Now, if we have 4 complex solutions, that means it comes in from the top, does some funny business, and goes out this way. So now when we look at the inequalities, if I change this right here, if I say I'm interested when is f of x greater than 0, I'll get one set of solutions. If I say when is f of x less than 0, I'll get another set. Right? Here we're talking about it being positive. In other words, we want to know when is this thing going to be positive. And then over here we're talking about when is it going to be negative. Now, just based on the information Mr. Adams has displayed on the screen, what would you say in the first scenario? When is this thing positive? All real numbers. All real numbers. When is this thing negative? So this would be all real numbers. And another way to list that would be, negative infinity to infinity. Now, when is this thing less than 0? Based on the graph. And I suppose, just to be fair, we should probably point out a couple of things. Positive occurs whenever we're above the x-axis, okay? When does negative occur? Negative occurs when we're below the x-axis, right? So when we're looking at the graph's y value is negative when we're below the x-axis, but when you look at my graph, because I have only complex solutions, that means I have no real solutions. That means that we don't intercept the x-axis. What do we know about the function? When is the function less than 0? It's never less than 0. Does that make sense? Now, there's lots of ways to write that. And I guess as we start to step up and become a little more formal, we would call this the empty set, because there is no value. It's a set of nothing, right? There's no solution. So we call that the empty set. Does that make sense? All right, so when you go to write your answer, if there's no solution, in addition to writing no solution, you would write empty set. Okay? That's it.